Which of the following statements about the additive Chi2 sampler in scikit-learn's kernel approximation methods is correct? A. Additive Chi2 sampler is a nonlinear transformation method that approximates a Gaussian kernel. B. It is primarily used for high-dimensional sparse data, like text data or images. C. Additive Chi2 sampler approximates the chi-squared kernel, known for its effectiveness in capturing nonlinear relationships. D. All of the above. A. Additive Chi2 sampler is a nonlinear transformation method that approximates a Gaussian kernel. Incorrect. Additive Chi2 sampler approximates the chi-squared kernel, not the Gaussian kernel. Additive Chi2 sampler approximates the chi-squared kernel, known for its effectiveness in capturing nonlinear relationships. B. It is primarily used for high-dimensional sparse data, like text data or images. Correct. Additive Chi2 sampler is specifically designed for handling high-dimensional sparse data due to the nature of the chi-squared kernel. 1. Text classification. Additive Chi2 sampler can effectively capture the semantic relationships between words in text data, making it suitable for tasks like sentiment analysis and topic modeling. 2. Image recognition. For image classification tasks, the non-linearity of the chi-squared kernel can help in capturing complex patterns and relationships between pixels, enabling better feature extraction. C. Additive Chi2 sampler approximates the chi-squared kernel, known for its effectiveness in capturing nonlinear relationships. Correct. Additive Chi2 sampler is a kernel approximation method designed to approximate the chi-squared kernel, which is indeed known for its ability to capture nonlinear relationships in data. Additive Chi2 sampler is designed to approximate the chi-squared kernel, which is known for its effectiveness in capturing nonlinear relationships in high-dimensional sparse data. D. All of the above. Correct. All statements A, B, and C are true about additive Chi2 sampler. Additive Chi2 sampler is designed to approximate the chi-squared kernel, which is known for its effectiveness in capturing nonlinear relationships in high-dimensional sparse data. 1. Text classification. Additive Chi2 sampler can effectively capture the semantic relationships between words in text data, making it suitable for tasks like sentiment analysis and topic modeling. 2. Image recognition. For image classification tasks, the non-linearity of the chi-squared kernel can help in capturing complex patterns and relationships between pixels, enabling better feature extraction. D. All of the above. A technique that approximates the results of a kernel function without explicitly calculating it. This is often used in high-dimensional settings where the computational cost of evaluating a kernel can be prohibitive. In large-scale machine learning tasks involving high-dimensional data, like image recognition or natural language processing, kernel approximation methods are crucial for reducing the computational overhead while maintaining accuracy. Functions that measure the similarity or distance between two data points in a high-dimensional feature space. Examples include the Gaussian kernel (RBF), linear kernel, and polynomial kernel. Kernel functions are widely used in support vector machines (SVMs) and other kernel-based learning algorithms. They allow these algorithms to learn complex, nonlinear relationships in data. A nonlinear kernel that is particularly well suited for handling sparse data, often used in document classification and image analysis. When dealing with text data represented as bag of words or images with pixel values, the chi-squared kernel can effectively capture the relationships between features, leading to improved classification performance. Data where most of the features have zero values, like text data represented as bag of words or images with pixel values. Many real-world datasets, especially those from text processing and image analysis, are sparse. Understanding and handling sparse data is crucial for effective machine learning. A popular Python library for machine learning, offering a wide range of algorithms, including kernel approximation methods like additive Chi2 sampler. Scikit-learn is a versatile and powerful library for machine learning practitioners, providing a wide range of tools for data preprocessing, model training, and evaluation. Algorithms that aim to approximate the results of kernel functions, reducing computational cost without significantly affecting performance. In scenarios where computational efficiency is a major concern, kernel approximation methods can provide a valuable alternative to explicitly computing kernel functions, enabling faster model training and prediction. Chi-squared kernel. The chi-squared kernel is a nonlinear kernel function that measures the similarity between two data points based on the distribution of their feature values. It's commonly used for sparse data, such as text data or images. Kx, y express gamma sumshi, yi to shi yi. In this formula, x and y are two data points. Shi and yi are their corresponding feature values. And gamma is a parameter that controls the width of the kernel function. The formula calculates the similarity between x and y based on the difference between their feature values, normalized by their sum. This normalization helps to handle sparse data where many feature values are zero. Consider two documents represented as bag of words vectors. x0, 1, 0, 2, 0, 1, y1, 0, 1, 1, 0, 0, using the chi-squared kernel. The similarity between these two documents would be calculated as follows. Kx, y express gamma sumshi, yi to shi yi express gamma o, 1201, 1, 0210, 1201, 2, 1221, 0200, 0210. Express gamma 1, 1, 1, 131. The resulting value would be a measure of similarity between the two documents, taking into account the differences in their word counts and the sparsity of the data. Which of the following statements are true regarding the Nystrom method for kernel approximation? In scikit-learn, A. It approximates the kernel matrix by sampling a subset of data points. B. It can be used to reduce computational complexity in kernel-based methods. C. It provides an efficient way to approximate the kernel map. D. All of the above. Subset sampling. This statement is correct. The Nystrom method works by selecting a subset of data points n from the original dataset n. It then computes the kernel matrix for these sampled points, which is much smaller than the full kernel matrix. This significantly reduces computational cost. True. Computational complexity. This statement is also correct. The Nystrom method is a technique designed to reduce the computational burden of kernel-based methods. It achieves this by approximating the full kernel matrix with a smaller, more manageable matrix. True. Kernel map approximation. This statement is true as well. The Nystrom method effectively approximates the kernel map, which essentially maps data points into a higher dimensional feature space. Instead of computing the full kernel map, it provides a computationally cheaper approximation. True. Answer. Since statements A, B, and C are all true, this option is the correct answer. The Nystrom method encompasses all these benefits. It approximates the kernel matrix by sampling, reduces computational complexity in kernel-based methods, and provides an efficient way to approximate the kernel map. True. D. All of the above. Kernel methods. Kernel methods are a family of algorithms that operate in a higher dimensional feature space using a kernel function. These methods leverage the concept of the kernel trick, which allows them to work implicitly in this high-dimensional space without explicitly computing the mappings. Kernel methods are widely used for tasks like classification, regression, and dimensionality reduction. In the context of image recognition, kernel methods like support vector machines (SVMs) can be used to classify images based on their underlying features, effectively differentiating images of cats from images of dogs. Imagine we have data points x1 and x2. A simple linear kernel would be defined as kx1, x2 by 1t x2, where x1t is the transpose of x1. This kernel calculates the dot product of the two vectors, providing a measure of similarity between them. Kernel functions. Kernel functions are crucial to kernel methods. They define the similarity measure between data points. Different kernel functions result in different underlying feature spaces and can impact the performance of the algorithm. Common examples include the Gaussian radial basis function (RBF) kernel, the linear kernel, and the polynomial kernel. In natural language processing, a kernel function might be used to measure the similarity between two sentences based on their word frequencies, helping to classify sentences as positive or negative sentiment. The RBF kernel is defined as kx1, x2 xp x1 x22 2 sigma 2, where x1 x2 is the Euclidean distance between the two vectors. The RBF kernel measures similarity based on the distance between data points in the original space. Kernel matrix. The kernel matrix K is a square matrix that stores the pairwise similarities between all data points based on the chosen kernel function. Each element Kij represents the similarity between data points I and j. In machine learning, the kernel matrix is used in algorithms like kernel PCA and kernel SVMs to perform operations in the implicit high-dimensional feature space. Given a dataset of 4 data points x1, x2, x3, x4, the corresponding kernel matrix would be a 4 by 4 matrix. For example, element K13 would represent the similarity between data points x1 and x3 calculated using a chosen kernel function. Kernel trick. The kernel trick is a key concept in kernel methods. It allows us to perform operations in the high-dimensional feature space without explicitly computing the feature mappings. Instead, we work with the kernel function, which implicitly encodes the inner products in that space. The kernel trick allows us to apply linear algorithms, such as linear SVMs, to nonlinear data, making kernel methods incredibly versatile. Kernel PCA. Kernel PCA is a nonlinear extension of principal component analysis (PCA). It uses kernel functions to find a lower dimensional representation of data in a nonlinear manner, making it suitable for data that is not linearly separable. Kernel PCA can be used to reduce the dimensionality of complex datasets such as those found in facial recognition, where subtle, nonlinear variations in facial features are important for identifying individuals. Unlike traditional PCA, which finds principal components in the original space, kernel PCA performs the analysis in the implicit feature space defined by the kernel function. Kernel SVM. Kernel support vector machines (SVMs) are powerful algorithms for classification and regression that leverage kernel functions to find optimal separating hyperplanes in the high-dimensional feature space. They are known for their ability to handle nonlinear relationships and generalize well to unseen data. In medical diagnosis, kernel SVMs can be used to classify patients based on their medical data, helping to predict the likelihood of a particular disease or condition. Kernel SVMs work by finding a hyperplane that maximizes the margin between classes in the feature space. This margin is defined by the kernel function, which measures the similarity between data points. Dimensionality reduction. Dimensionality reduction is a technique used to reduce the number of features in a dataset while preserving the important information. This can be beneficial for improving the efficiency of learning algorithms and reducing the impact of the curse of dimensionality. In text mining, dimensionality reduction techniques can be used to represent documents as vectors in a lower dimensional space, enabling efficient comparison and clustering of documents. Computational complexity. Computational complexity refers to the resources, time and memory required by an algorithm to complete a task. In machine learning, algorithms with high computational complexity can be challenging to train, especially on large datasets. In real-time applications like autonomous driving, computational complexity is a critical factor. Algorithms must be able to process data quickly to make decisions in real time. You are building a machine learning model for predicting customer churn. Your dataset includes a large number of categorical features that you need to transform into numerical features for your model. Which of the following is a suitable approach for efficiently approximating a polynomial kernel? Using polynomial count sketch. Use a simple one-hot encoding scheme to convert categorical features into numerical features. Apply a hashing trick to map categorical features into a lower dimensional space. Use a random Fourier features RFF approach with a polynomial kernel function. All of the above. One-hot encoding is a simple approach for converting categorical features into numerical features. It works by creating a binary vector for each category. While it's straightforward, it can lead to high dimensionality in the feature space, which might not be ideal for handling large datasets. Polynomial count sketch can be used to efficiently approximate polynomial kernels, even with high dimensional data. True. A. Use a simple one-hot encoding scheme to convert categorical features into numerical features. The hashing trick maps categorical features into a lower dimensional space using a hash function. It's more efficient than one-hot encoding, but it might result in collisions, different features mapping to the same hash value, which could lead to information loss. Polynomial count sketch can be used to efficiently approximate polynomial kernels, even with high dimensional data. True. B. Apply a hashing trick to map categorical features into a lower dimensional space. Random Fourier features RFF uses a specific class of functions, e.g., sinusoidal, to approximate the kernel. The choice of kernel function in RFF can influence the approximation accuracy. Using a polynomial kernel in RFF can lead to an effective representation for polynomial kernels. Polynomial count sketch can be used to efficiently approximate polynomial kernels, even with high dimensional data. True. C. Use a random Fourier features RFF approach with a polynomial kernel function. All the techniques mentioned above, one-hot encoding, hashing trick, and RFF with polynomial kernels, can be used effectively in polynomial count sketch to approximate polynomial kernels. Each method contributes differently to the overall process. One-hot encoding provides a basis. Hashing trick reduces dimensionality, and RFF with polynomial kernels offers a specific approximation method. Polynomial count sketch can be used to efficiently approximate polynomial kernels, even with high-dimensional data. True. D. All of the above. D. All of the above. Kernel approximation. Approximating a kernel function to make computations faster. Working with high-dimensional data where computing exact kernel values is computationally expensive. Kernel approximation. Polynomial kernel. A kernel function that measures the similarity between data points based on polynomial relationships, capturing nonlinear relationships between features. Polynomial kernel. Polynomial count sketch. An algorithm for approximating polynomial kernels. Efficiently calculating kernel similarity for high-dimensional data. Polynomial count sketch. One-hot encoding. Converting categorical features into numerical features by creating a binary vector for each category. Transforming categorical features into a suitable format for machine learning models. One-hot encoding. Hashing trick. Mapping categorical features to a lower dimensional space using hash functions. Reducing dimensionality and handling large feature spaces. Hashing trick. Random Fourier features RFF. A method for approximating kernel functions using random linear combinations of basis functions. Approximating kernels for faster computation and dimensionality reduction. Random Fourier features RFF. Imagine you have a dataset with a categorical feature region with values like north, south, east, and west. You can use one-hot encoding to represent this feature numerically. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Each category is assigned a unique binary vector. This approach can be useful in polynomial count sketch, but it can also lead to high dimensionality, especially with many categories. You have a dataset with a large number of features. You want to use a support vector machine SVM classifier. But training on the original data takes too long. How can you speed up the process while maintaining good performance? Use principal component analysis (PCA) to reduce dimensionality. Apply feature selection techniques. Utilize kernel approximation methods like RBF sampler. All of the above. PCA principal component analysis (BR) reduces dimensionality by identifying the most important features. It transforms the data into a lower dimensional space while retaining as much variance as possible. True. PCA helps reduce the number of features in the dataset, thereby reducing the computational complexity of training the SVM. By preserving the most significant variance, PCA aims to retain as much information as possible from the original features. Feature selection (BR) chooses the most relevant features based on their importance. This can be achieved using methods like recursive feature elimination (RFE) or univariate feature selection. True. Feature selection techniques, like recursive feature elimination (RFE) or univariate feature selection, directly eliminate less informative features from the dataset, effectively reducing the dimensionality and simplifying the training process. Kernel approximation RBF sampler (BR) approximates the kernel function used by SVMs, leading to faster training. This is particularly beneficial when dealing with high-dimensional datasets. RBF sampler is a method that approximates the radial basis function RBF kernel using random Fourier features. True. Kernel approximation methods, such as RBF sampler, address the computational bottleneck associated with kernel evaluations. They approximate the complex kernel function, leading to faster training. RBF sampler specifically uses random Fourier features to efficiently approximate the radial basis Function RBF kernel. The correct answer is D, all of the above. True. All the above choices offer effective strategies for handling high-dimensional datasets, each contributing to faster training times for SVMs. PCA reduces dimensionality. Feature selection removes irrelevant features. And kernel approximation simplifies kernel calculations. D. All of the above. SVM support vector machine supervised learning algorithm used for classification and regression. SVMs find an optimal hyperplane that separates data points into different classes. SVMs are powerful algorithms for classification and regression, known for their ability to find optimal decision boundaries between classes. They work by finding a hyperplane in a high-dimensional feature space that maximizes the margin between data points of different classes. Kernel function bra function that measures the similarity between two data points. It transforms the data into a higher dimensional feature space, enabling nonlinear separation. Kernel functions are crucial for SVMs, particularly when dealing with non-linearly separable data. They allow SVMs to find optimal hyperplanes in a higher dimensional space by mapping the data points into a more suitable feature space, where linear separation is possible. RBF radial basis function kernel bra common kernel used in SVMs, which measures similarity based on the Euclidean distance between data points. The RBF kernel is a popular choice for SVMs, measuring similarity between data points based on their Euclidean distance. It provides a good balance between computational efficiency and the ability to model nonlinear relationships. Random Fourier features BRA technique used for approximating kernels. It transforms the data into a lower dimensional space by randomly projecting it onto a set of Fourier features. Random Fourier features provide an efficient way to approximate kernel functions. By randomly projecting the data onto a set of Fourier features, they reduce the dimensionality of the problem, enabling faster kernel computations. Image recognition. Large datasets with many pixels using kernel approximation can significantly speed up training. Image recognition often involves handling massive datasets with thousands of pixels, making training SVMs computationally demanding. Kernel approximation methods, such as RBF sampler, can significantly speed up the training process by simplifying kernel calculations. Text classification. Handling high-dimensional text data, e.g., using TF-IDF. Kernel approximation can reduce the computational complexity of training. Text classification tasks often involve high-dimensional text data, represented using methods like TF-IDF, term frequency, inverse document frequency. Kernel approximation methods can effectively reduce the computational complexity associated with training SVMs on such large datasets. Bioinformatics. Analyzing high-dimensional genomic data. Kernel approximation is useful for handling large datasets with complex features. Bioinformatics analyses often involve complex datasets with a vast number of features, such as genomic data. Kernel approximation techniques can be valuable for handling such high-dimensional data, enabling faster training of SVMs for tasks like gene classification or protein function prediction. You are working on a large-scale classification problem with high-dimensional features. You want to apply a kernel method like the support vector machine SVM but are facing computational limitations. What technique can you use to approximate the kernel function for faster computation? A. Linear discriminant analysis (LDA). B. Kernel approximation using random Fourier features. C. Kernel approximation using Nystrom method. D. Kernel approximation using skewed Chi2 sampler. E. All of the above. A. Linear discriminant analysis (LDA). Incorrect. LDA is a linear dimensionality reduction technique used for classification. It does not directly approximate kernel functions. While it can be used in combination with kernel methods, it is not a kernel approximation technique itself. B. Kernel approximation using random Fourier features. Correct. Random Fourier features is a technique that approximates a kernel by mapping data points to a lower dimensional space using random projections from the Fourier transform of the kernel function. It is specifically used to speed up computations in kernel methods with high-dimensional data. C. Kernel approximation using Nystrom method. Correct. The Nystrom method is another common kernel approximation technique. It approximates the kernel by selecting a subset of data points called landmarks and using them to construct the low-rank approximation of the kernel matrix. This reduces computational complexity while preserving essential information from the original kernel. D. Kernel approximation using skewed Chi2 sampler. Correct. The skewed Chi2 sampler is specifically designed for approximating the chi-squared kernel, which is a popular kernel for text and document analysis. It generates random projections from a skewed chi-squared distribution, leading to a faster computation of the kernel. E. All of the above. Correct. All of the techniques mentioned are valid kernel approximation methods used to reduce computational complexity in kernel methods, especially in high-dimensional datasets. E. All of the above. LT font style font size 14px GT LTBGT kernel methods LTBGT. These methods aim to implicitly map data into higher dimensional feature spaces called kernel spaces using a kernel function. This allows for nonlinear decision boundaries in classification or regression. Examples include SVM and Gaussian processes. LT font GT. Imagine you have data points that are not linearly separable in a 2D space. A kernel method like SVM could map these points to a higher dimensional space, e.g., 3D, where they become linearly separable. The kernel function defines how the data is transformed to this higher dimensional space. LT font style font size 14px GT LTBGT kernel function LTBGT, a function that measures a similarity between two data points in a high-dimensional space. Common kernels include the Gaussian RBF kernel, polynomial kernel, and sigmoid kernel. LT font GT. The Gaussian kernel is often used in SVM. It measures the similarity between two data points based on their distance in the high-dimensional feature space. The closer the points are, the higher the similarity, and vice versa. LT font style font size 14px GT LTBGT kernel approximation LTBGT techniques that aim to approximate the kernel function in a lower dimensional space. This is done to speed up computations, especially in high-dimensional datasets. LT font GT. Consider a dataset with millions of data points. Calculating the kernel function for every pair of data points would be computationally expensive. Kernel approximation techniques like random Fourier features aim to find a faster and more efficient way to approximate the kernel function, reducing the computation time significantly. LT font style font size 14px GT LTBGT SKEWEDCHI2 sampler LTBGT, a specific kernel approximation technique used in scikit-learn sklearn for approximating the chi-squared kernel. LT font GT. Imagine you have a text dataset with a large vocabulary. Using the skewed Chi2 sampler, you could approximate the chi-squared kernel, which is suitable for comparing text documents based on their word frequencies. This would be faster than computing the full chi-squared kernel directly. LT font style font size 14 px GT LTBGT CHI squared kernel TBGT, a kernel function that measures the similarity between two data points based on their frequency distributions. It's often used for text and document analysis. LT font GT. Imagine two documents with similar word frequencies. The chi-squared kernel would give a high similarity score, indicating that these documents are likely similar in topic. It is widely used in text classification, document retrieval, and information retrieval. LT font style font size 14 px GT LTBGT random Fourier features LTBGT, a kernel approximation technique based on the Fourier transform. It maps data points to a lower dimensional space using random projections generated from a Fourier transform of the kernel function. LT font GT. In a large image recognition problem, using random Fourier features to approximate a kernel function, e.g., the Gaussian kernel, could significantly speed up the training of a deep learning model, making it practical to work with massive datasets. LT font style font size 14 px GT LTBGTNE's TRM method. LTBGT, a kernel approximation technique that uses a subset of data points called landmarks to construct the low-rank approximation of the kernel matrix. LT font GT. In a recommender system, the Nystrom method could be used to approximate the kernel function for finding similar users or items by selecting a smaller set of landmarks. The computation of the kernel becomes more efficient, leading to faster recommendations. LT font style font size 14 px GT LTBGT linear discriminant analysis LDA LTBGT, a dimensionality reduction technique that aims to find a set of axes that best separate the classes. It is not directly related to kernel approximation but is a commonly used technique for classification and dimensionality reduction. LT font GT. In facial recognition, LDA could be used to reduce the dimensionality of facial images by finding axes that best separate different individuals. This could be a preprocessing step before applying a kernel-based classification algorithm.